Process scheduling. In process scheduling, we learn basic CPU scheduling and some CPU scheduling algorithms. By switching the CPU among processes, the operating system makes the computer more productive. So here, we are going to learn different scheduling mechanisms to do this. In a uniprocessor system, only one process can run at a time. Processes are brought into memory and they are kept in the ready queue. And one by one, they are allocated to the processor. Typically, processes alternate between two states, CPU burst and IO burst. Processes begin with a CPU burst, followed by an IO burst, then again followed by a CPU burst, then another IO burst, and so on, and finally a CPU burst, and then the process terminates. Now, when the process goes for an IO request, CPU remains idle, CPU time is wasted. So, what does the OS do? He will allocate the next process to the CPU. So, every time one process leaves the CPU to do something else or it exits, a different process is allocated to the CPU to keep the CPU busy. That is, you are maximizing CPU utilization. The selection of a process is done by the short-term scheduler. It is this scheduler that selects a process from among the processes in the ready queue and allocates the CPU to that process. It does this choice based on different criteria. We are going to learn different algorithms for this. CPU scheduling decisions happen under four circumstances. One, when a process switches from the running state to the waiting state. Two, when a process switches from the running state to the ready state. Three, when a process switches from the waiting state to the ready state. And four, when a process terminates. In case 1 and 4, another process, if there is one in the ready queue, is selected for execution. In case 2 and 3, you can make a choice of either scheduling another process or scheduling this old process. When scheduling occurs in case 1 and 4, it is called non-preemptive or cooperative. Otherwise, it is preemptive. So what is non-preemptive? Once the CPU is given to a process, the process keeps the CPU until it voluntarily releases it. That is either by terminating or moving to the waiting state. This is called non-preemptive. Under preemptive, the process is stopped or interrupted from executing under certain circumstances. Now, let us go through some characteristics or criteria used for comparing different algorithms. This will help us to judge the best algorithm. The first one, CPU utilization. Our aim here is to keep the CPU busy all the time. Usually, the range is from 40%, that is a lightly loaded system, to 90% for a heavily loaded system. Next, throughput is the number of processes that are completed per unit time. Third, turnaround time. Turnaround time is the interval from the time of submission of a process to the time of completion of that process. That is the time from arrival to completion. Next, waiting time, the amount of time that a process spends waiting in the ready queue. And finally, response time is the time from the submission of a request until the first response is produced. Response time is mainly important in interactive systems where The time it takes to start responding is important, not the time it takes to output the response. So, we are always trying to maximize CPU utilization, maximize throughput, minimize turnaround time, minimize waiting time, and minimize response time. Let us go through the first basic CPU scheduling algorithm, which is called first come, first serve algorithm, FCFS scheduling algorithm. The example that is taken is from Galvin textbook. FCFS scheduling algorithm schedules processes based on their arrival time. The process which arrives first in the ready queue will get the CPU first. The earlier the arrival time, the sooner the process gets the CPU. Some of the features of first come, first serve are: it is simple and easy. It is easy to implement it programmatically. You just have to use the queue data structure where a new process enters through the tail of the queue and the scheduler selects the process which is at the head of the queue. FCFS is non-preemptive. Now, because of its non-preemptive nature, the problem of starvation may occur. That is, if the first process is the longest among all the other processes. In FCFS, priority of a process is not considered. Also, the average waiting time is higher as compared to other scheduling algorithms, and FCFS suffers from convoy effect. Let us go through the example. In this example, we have considered three processes, P1, P2, P3. P1 has a burst time or execution time of 24 units, P2 3 time units, and P3 3 time units. We are going to assume that the arrival order is P1, P2, and P3. So first in FCFS, P1 is going to be scheduled from time 0 to 24. Next, P2 from time 24 to 27, followed by P3 from time 27 to 30. This is shown in the Gantt chart on the screen. Now we compute the average turnaround time and average waiting time. For that, first we compute the turnaround time of each process. Turnaround time is given by finish time minus arrival time. Waiting time is given by turnaround time minus burst time. So the turnaround time for process P1 is finish time, that is 24, minus arrival time, that is 0, which is equal to 24. Turnaround time for P2 is 27 minus 0, which is 27. And turnaround time for P3 is 30 minus 0, which is 30. The average of 24, 27, and 30 is 27 time units. So the average turnaround time is 27 time units. The waiting time is turnaround time minus burst time. So for P1, it is turnaround time of 24 minus burst time 24, which is 0. For P2, it is 27 minus 3, which is 24. And for P3, it is 30 minus 3, which is 27. The average waiting time is the average of 0, 24, and 27, which is 17 time units. This is all with respect to first come, first serve scheduling. Thank you.